Imagine going through your entire life completely deaf. No sound, no music, no voice. And then, one morning, waking up to hear the world for the very first time. Every rustling leaf, every distant thunderclap, every conversation that had always been happening just beyond reach, suddenly pouring in. That is the closest analogy to what happened to science on September 14th, 2015. Humanity, for the first time in its history, heard the universe. For thousands of years, every single thing known about the cosmos has arrived through light. Visible light through optical telescopes, radio waves through dish arrays, X-rays and gamma rays through space-based observatories. All of it electromagnetic radiation, all of it the same fundamental phenomenon. Every star catalog, every galaxy map, every image of a nebula or a black hole's silhouette, all built from photons, particles of light. The entire architecture of modern astronomy rests on that single sensory channel. And then, on that September morning, a second channel opened. Gravitational waves are ripples in the fabric of space-time itself. To understand what that means, it helps to step back to 1915 when Albert Einstein published his general theory of relativity. In that framework, gravity is not a force reaching across empty space the way Newton imagined. Gravity is the curvature of space-time, the four-dimensional fabric in which the entire universe exists. Massive objects warp that fabric the way a bowling ball placed on a stretched rubber sheet creates a depression. Other objects then follow curved paths through that warped geometry, and what appears to be a gravitational pull is simply the shape of the space they're moving through. Einstein went further. He predicted that when massive objects accelerate, particularly when they orbit each other or collide, they should send ripples outward through that fabric, like the waves spreading across a pond when a stone breaks the surface. These ripples would travel at the speed of light, carrying energy and information across the cosmos. He predicted them. And then, almost in the same breath, he doubted they could ever be detected. The warping of space-time they would produce, even from catastrophic cosmic events, would be so extraordinarily small that no instrument imaginable in 1915 could possibly register it. He was right about the scale of the challenge. When that signal arrived in 2015, it had been produced by two black holes, one roughly 29 times the mass of the Sun, the other 36 times, spiraling toward each other over billions of years, accelerating to nearly half the speed of light in their final moments, and then merging in a collision that released more energy in a fraction of a second than all the stars in the observable universe combined. That event, 1.3 billion light years away, produced a gravitational wave that, by the time it reached Earth, distorted the distance between two mirrors 4 kilometers apart by less than 1/10,000th, the diameter of a single proton. The detectors at LIGO, the Laser Interferometer Gravitational Wave Observatory, and measured that. The precision involved is almost philosophically disorienting. It is the equivalent of measuring the distance from Earth to the nearest star with an accuracy of less than the width of a human hair. And the signal itself, converted to sound so human ears could process it, was a chirp, a rising tone, less than a second long, that swept upward and then vanished. Scientists called it, informally, the chirp of two black holes kissing, a billion years of cosmic drama compressed into a sound a person could hold in their hand. The excitement that erupted through the scientific world when LIGO announced the detection in February 2016 was not merely the joy of confirming Einstein's last great unverified prediction, though that alone would have been extraordinary. The deeper thrill was the recognition of what had just become possible. Every discovery in astronomy up to that point had been limited by what light could tell. And light has serious limitations as a cosmic messenger. It can be absorbed, scattered, or blocked by dust clouds and gas. Sources that produce little or no light, like black holes before they merge, or the universe in its first 380,000 years before atoms even formed, are effectively invisible to every electromagnetic telescope ever built. Gravitational waves pass through everything: dust, gas, planets, stars, entire galaxies. None of it impedes them. They carry information from regions and events that are permanently hidden from light-based observation. The very early universe, the instant after the Big Bang, the deep interior of collapsing stars, the merger of neutron stars in distant galaxies, all of these generate gravitational waves that arrive here uncorrupted, carrying the direct imprint of what produced them. Astronomy with gravitational waves is astronomy without blindfolds, and the universe, it turns out, has been extraordinarily loud. Since that first detection, LIGO and its partner observatory Virgo have cataloged dozens of merging black holes, colliding neutron stars, and events that may represent entirely new categories of object. The neutron star merger detected in 2017 was observed simultaneously in gravitational waves and across the full electromagnetic spectrum, a moment scientists called multi-messenger astronomy. And in those combined signals, researchers found direct evidence that heavy elements like gold and platinum are forged in exactly these kinds of violent collisions. Every gold ring on every finger on Earth was born in an event like the one detected that day. The philosophical weight of this shift is worth sitting with. For all of recorded history, humanity has been a purely visual species when it comes to understanding the cosmos. Every cosmological model, every theory of the universe's origin and fate has been built from the light that reached human eyes and the instruments that extended them. Gravitational wave astronomy does not simply add new data to that picture, it opens an entirely different kind of picture, painted in a medium that existed all along but was utterly beyond reach. It is the difference between a world perceived only through sight and a world where hearing suddenly becomes possible. The landscape has not changed, the capacity to perceive it has. What makes this the most profound scientific achievement of the 21st century, arguably of any era since Galileo first tilted a telescope toward the sky, is precisely this. The universe did not change on September 14, 2015. Gravitational waves had been crossing Earth for its entire existence. Undetected, unheard, black holes had been merging in the darkness, sending their signatures through spacetime toward a planet that had no way to receive them. On that morning, the planet finally did. And in the silence that followed the chirp, that brief rising tone from 1.3 billion years away, the universe became, for the first time, fully addressable. What was always there, but unreachable, became knowable. And that, more than any single fact it has yet revealed, is why the detection of gravitational waves marks a true before and after in the story of human understanding.